So in this talk, I want to share some of the things that we found to be useful for the league, and most of them are in software part. But I have some technical things. So obviously, it's based on two things: hardware and software. In hardware, we changed two major things this year. We put a gyroscope sensor on our robots, and we changed our wireless transmitting. So gyro is obviously a device, a sensor that outputs angular velocity. We use it for some reasons. One of them is we have latency in the small size league that everything is finding a new way for overcoming this. So for positional prediction, we have some good methods like using Kalman filter. But for angular prediction, we found that using gyroscope is an accurate way for overcoming the latency. So we use it in two situations. One to overcome no vision, vision latency and other latencies. And one is for when the robots, the vision does not detect the robot. We can predict the robot in these situations using the commands sent to the robots, but the angle is completely unknown in this situation. So we use the gyroscope to predict the angle up to maybe 10 seconds or 15 seconds. So we can run our robots up to 10 seconds with no vision data to some points. One other thing is calculating the delta margin shooting that was used by CM Dragon's team, and we evaluate the things that use ball position and other things in our AI and send the evaluation points to the robot, and the robot calculates the other part of the delta margin that uses the robot's angle, and it should be completely accurate. And then if the delta margin shooting results that the robot should kick the ball, it kicks the ball. One other thing is that we sent global commands, weeks and video commands into the robot, and the robot transforms it to its local frame and then send it to the PID loop. And one other thing is that we use a PID, alter PID loop on the mobile sent from the AI. And also we changed our wireless communication this year. The main reason for this was that our previous modules has very low bandwidth. So this year we use NRF modules that's being used by many other things in this league. But we also changed our interface board for robot communication, and the new interface board uses LAN protocol for communicating to the AI. It receives a command over UDP and just UDP, and sends the data to robots and gives the feedbacks and sends it to the IP that requested as feedback from the robots. One of its major improvements is that many AI computers can connect to the network and send the command data to the communication board, and it sends back the feedback data, and they can work completely with no interference with each other. And one other thing this board does is it can automatically calculates the data loss in this frequency for all the AI computers that are connected to this board, and then it sends the data loss back, and the AI detects the interference, and it just calculates the interference. It does nothing, because it can cause many problems if it automatically changes the frequency. And if there's any interference, we can change the frequency of the board, and the robots automatically detects search for the frequency and detect frequency that the transmitting board are sending the command. So in software part, one of the main things we tried to do was to overcome the performance bottleneck that that currently many teams I think have in the league. You know that SSL was started in 1997, and back then Pentium CPUs were used for doing AI computations. And back then, I think the frequency that Vision was working was 30 Hz, and now it's 60 Hz. And it's just double the frequency, but the CPUs we are using now are Core i7 that are thousands of times faster than the CPUs back then. But you can see that many teams are carrying heavy PCs and very powerful PCs so they can run their AIs. So I think one of the things that many people do not know is that the new bottleneck for the computations is the memory, not the processor. As you can see here, the processor from 1980 to 2010 have grown in performance very rapidly, and they're tens of thousands faster than them. But the memory is growing in a different pace. So now the memory is the bottleneck. As you can see from our test, the read from the memory takes about 1600 cycles of CPU at 3.2 GHz. That's a lot of cycles for the CPU. So one of the things that we can do for overcoming this situation is using data-oriented design in our code. Data-oriented design is in the situations we know the data that is being processed, we can do our code and develop our code around this data. And, this means we place the data that is being transferred between different modules in our software, and we develop our code around this data. Not that we develop our code and maybe some data is traveling between. I think in this example, I can tell you what this means. Here we have an example robot class that has some position in current direction, and it has to aim to some direction that maybe it's calculated from higher levels in AI. So if we write it in object-oriented method, we have an aim function in our robot that takes a target point, it's a vector 2, and it calculates the direction that robot must take with some angle with function that is somewhere else. But here, if the aim function is called many times, the CPU have to cache all the robot class, including position, direction, target direction, and many other parameters in a robot class, maybe the battery voltage that is not being used in the aim function. The CPU cache all these things and then calculates the direction for this robot, and then puts all the cache data out and cache the other robots in. So there is a lot of cache missing here, and the performance will be too bad. But if we develop our code in data-oriented fashion, it will be one aim function that receives an array of position, target direction, and target points, and the count of them, and then it in a loop it calculates all the target direction for all robots in just one function. What's happening here is the CPU just cache the position, target direction, and targets that it needs to be calculated in this function, and there is much less cache miss here. So the performance will be a lot better. In our test, it's much better in this fashion of coding. One other thing we did to work on the performance bottleneck was moving some of our calculation to the GPU. So the current method, we previously used CUDA and OpenCL for computing the evaluations and many other things on the GPU, but they're not really good. And as you may know, we are doing our AI on Mac, and CUDA is not really good on Mac. It's better for Windows and maybe Linux. So now we are using OpenGL, raw OpenGL, and we use shaders, fragment shaders for calculating evaluation and other things, and then we use the read pixel functions of OpenGL to take the data back to the main memory. So here you can see that it's a field evaluation for computing the best point for receiving a pass and the The brighter each point is better for receiving pass, and the red point in the middle is the best one calculated. Another thing we use on the GPU is calculating the safety for each point of the field, and then using this in our pass planning method. So as a result, our AI and vision filtering is running around 2.2 milliseconds on a laptop, on average laptop. And it really makes it possible for doing much more interesting AI things and developing AI. And one of the things we don't have to carry heavy pieces compositions. One of the things we did is a new pass planning method. It's called SPRRT. We use it since 2010, and it biases the RRT tree to safer areas. It's been explained last year, so I won't go into details of this. But the main problem with this method is its performance bottleneck. It's not a bottleneck. It's not a problem in the SSL Small Size League, because here we have just at maximum 12 robots and 12 obstacles, so there's not many problems with the performance. But we use SSL as just a test bed for our method, so we have to push it to the best performance level we can. And as we can prove it, computation time in the SPRRT increases linearly with the number of obstacles. So we use artificial neural network to remove the obstacles that are not important for the pass being planned. So here you can see that only red obstacles are being used in the planning stage, and all other obstacles that you can see are removed from the planning. And we tested this year, and there's no much glitches or collisions with this method. So I think it's doing just fine for us. And for prediction, we also use artificial neural network that's being used by Foo Fighters in, I think in 2004. And it's a lot better than linear prediction that we were using last year. And we also use this method for removing latency, and also we can predict our robots to maybe have that 10 seconds I mentioned earlier for just positions. So that's it in person.
Okay, thank you. Oh, no, I'm not going to.
Have you, how do you merge the data from vision and gyro? Did you use any kind of, data fusion?
We wanted to implement the column filter on robots, but the processing is much easier. Yeah, but we just, if the robot is seen by the vision, we trust the vision and use that as the trusted angle for the robot. And robots just predict it from 150 milliseconds. But if there is just one frame, the vision doesn't see the robot calculates its own angle from the previous vision data.
So you use a kind of if then data fusion, and it works well.
Yeah.
Oh, thank you so much, Ali. Next up and last is Robo Dragons. I think, yes. Robo Dragons.